Welcome to science class. Today, we are going to learn about the structure and composition of the universe. To do this, we have to go beyond just planets or stars or solar systems or even the Milky Way. Those objects are too small. We have to go really big picture. Let's do just that for the introduction here and zoom out all the way. The Milky Way is part of a collection of galaxies unimaginatively named the Local Group. The Local Group consists of at least 80 galaxies. The Milky Way and Andromeda are the only large spiral galaxies. The rest are so-called satellite galaxies, dwarfs, irregulars, and such. The size of the local cluster is around 3 million light-years across. The reason we call this a cluster is because these galaxies are all moving towards one another. I've mentioned this before, but it's confusing. Space is expanding, but gravity causes objects with mass to be attracted to one another, so they can close the space between them. The observable universe is unthinkably large, close to 100 billion light-years across. So yes, a cluster of galaxies that are spread out over only 3 million light-years is in a small enough space to allow mutual gravity to attract them. On an even larger scale, local clusters form larger galaxy clusters, which in turn form superclusters. Galaxy cluster IDCS J1426 is 10 billion light-years away and has a mass of around 500 trillion suns. The Milky Way contains somewhere between 100 and 400 billion stars, but most galaxies are much smaller dwarfs. Assuming an average galaxy has 100 million stars, this would mean cluster IDCS contains something like 5 million galaxies. The Milky Way is a member of the Virgo supercluster. In this video, called the Cosmic Eye, you can see that these superclusters form networks or webs of galaxies. This is the result of a uniform universe at the Big Bang, spreading out over billions of light years, and gravity causing that matter to clump into unimaginably large, gravitationally bound systems. Makes you feel kind of small, doesn't it? Let's get started. Where we left off in the last video was the discovery of dark matter. The short version of this is that galaxies rotate far too fast for the stars and gas within them to be held on by the gravity of the collective stars and gas within the galaxy. Normal matter only accounted for 15% of the gravitational strength required to keep these galaxies together. Today we know that dark matter extends well beyond the edges of galaxies. The Milky Way has a gigantic halo of dark matter that extends beyond the apparent edge. The superclusters and webs we peered at earlier are believed to be a result of the much more present dark matter in the universe organizing the galaxies into those superstructures. Without dark matter, galaxies couldn't form clusters over the tremendous distances that they do. The origins of dark matter predate Vera Rubin, who studied galactic rotation closely by several decades. In the 1930s, a Swiss astronomer named Fritz Zwicky observed the Coma cluster, a group of some 1,000 galaxies. He concluded that, based on what was visible, the cluster should not be able to exist. The galaxies should not be gravitationally bound, they should fly apart. Zwicky coined the term dark matter to account for something that accounted for most of the gravity but could not be detected. Zwicky's initial estimates were way too high, but he was basically vindicated by the work of Rubin. At first, astronomers assumed the Coma cluster anomaly would be answered by new or better technology that can see something that was previously hidden, but that never happened. Maybe it was just a lack of precision in the measurements. But the most precise measurements still show that visible matter can't account for all the gravity. Maybe it was some new form of matter or black holes. Nope. Eventually, astronomers had to accept that something outside of the known laws of physics and the standard model of particles, which describe matter itself, was responsible. We have absolutely no idea what dark matter is. Whatever it is, it's not matter, and it's not antimatter either. Dark matter won't interact with electromagnetic radiation or standard matter, except for the fact that it has gravity. According to Einstein, space is not empty, it is made up of fields. Objects with mass warp the fabric of space and time, and this is responsible for the force of gravity. The warping of space-time can cause an object to travel in a straight line that is also a curved line. If you travel in a straight line on Earth, eventually you circle back around to where you started, a curved path. A straight line transplanted onto a cone draws a curve, and vice versa. Those are just examples, they're not the product of relativity. Massive objects can cause light to be deflected, even though the light itself travels in what it considered a straight line. Because of this phenomenon, we can see objects that are just behind the edge of the sun, because light wraps around it. Although we can't see dark matter, we can detect its gravitational influence. We've already discussed the rotation of galaxies and galaxy clusters, but there's also gravitational lensing. Gravitational lensing is just like the warping of light around the sun, but more extreme. When we try to observe galaxies and galaxy clusters that are behind others, we see that their light becomes distorted to a ridiculous level, like funhouse mirror kind of ridiculous. This is yet another set of confirmations of dark matter's presence. This really humbled and bothered physicists. 85% of the stuff that has gravity in the universe is undetectable. We don't know what it is. The stuff we thought made up everything makes up a rather small portion of the universe. But it gets even worse than that because there's also dark energy. Recall Hubble's observation and the Hubble-Lemaitre law, which states that the more distant a galaxy is, the faster it retreats away from us. On the local level, yes, galaxy clusters form, and so Andromeda is heading towards us, but the universe is billions and billions of light years across, if not infinite. But even though the universe is expanding, there is so much matter, and even more dark matter, that astronomers predicted that the expansion rate of the universe has to be slowing down. Except it isn't. The expansion of the universe is accelerating, not static, accelerating. This was the single most unexpected discovery in all of astronomy. It simply flies in the face of logic. Once again, we have no clue what dark energy is. What dark energy seems to be is a property of space itself. There's a tiny amount of energy which occupies every cubic meter of space. Like an insanely tiny amount of energy. But the universe is composed of so many countless cubic meters of space that the sum of all of this dark energy may be the thing that allows space to expand at an ever-increasing rate. So the overall composition of the universe looks something like this. Around 68% dark energy, 27% dark matter, and only 5% normal matter and energy. 5%. Will the universe simply expand forever? Or will the expansion of the universe at some point slow down, even reverse course and lead to a sort of reverse Big Bang? How will the universe end? To be clear, we don't really know that either. The most likely candidate appears to be what's called heat death. In this scenario, the universe expands so much that eventually particles can no longer interact with one another. Particles also decay into pure energy over long periods of time. And by long periods of time, I mean something like 10 to the 100th power years from now. That's the time frame of when heat death would occur. At that point, remaining particles would be so spaced apart that they could never interact or undergo chemical reactions. Nothing would ever change. Time would become meaningless. Like I said, it's not for a long time, so don't worry about it. I read this book not too long ago, The End of Everything. It's a great book on the structure of the universe and all of the ways it may possibly end. So you will now notice that we have just come to the end of the universe. Logically speaking, that's pretty much the end of this class as well. I mean, if we've hit the end of the universe, what else could we possibly talk about? I do have one more video for you to wrap things up, but I want to talk about the expansion of the universe a bit more because there's a fascinating little quirk about the expanding universe. I've said this before, and you may already know this, but when you look at distant objects, you are looking back in time. If you were on a cell phone with somebody on the moon, you wouldn't hear what they're saying in real time. There's about a 2-second delay. Information can only travel at or slower than the speed of light. It takes between 5 and 20 minutes for radio signals to reach Earth that are broadcast from Mars. But it's the same with visible light. When you see an object 1 light year away, you see it as it appeared 1 year ago. When you see an object 1,000,000 light years away, you see it as it appeared 1,000,000 years ago. We know the universe is 13.77 billion years old, but we can see objects that are about 45 billion light years away. Now, how is that possible? At certain distances, the universe is expanding faster than the speed of light. But billions of years ago, those objects that are now very far and traveling very fast were much, much, much closer. A galaxy that in this present moment in time is 13.77 billion light years away or more is too far and moving too fast for us to ever see. If it is closer than that, we can see it. We won't see it instantaneously. It will take billions of years for the light to reach us, but it will eventually reach us. Similarly, if somebody sent a radio signal to Earth from 13.6 billion light years away, it would take billions of years to reach us. But because the universe is always expanding, by the time it gets to us, the gap between us and whatever we are observing is so much greater. So instead of taking 13.6 billion years for that radio signal to get to us, it takes far longer. We can only see backwards in time 13.77 billion years, but because space is expanding, distance in light years and distance backwards in time don't always match up. This reminds me of an amazing mathematical puzzle, the ant on a rubber rope. Here's the basic premise. An ant starts to crawl along a taut rubber rope 1 kilometer long at a speed of 1 centimeter per second relative to the rubber it's crawling on. At the same time, the rope starts to stretch uniformly at a constant rate of 1 kilometer per second. So after 1 second, it's 2 kilometers long, after 2 seconds, it's 3 kilometers long, etc. Will the ant ever reach the end of this rope? It seems impossible. The ant is moving thousands of times slower than the speed at which the rope stretches. But the answer is yes. In this specific case, it takes forever. 8.9 times 10 to the 43,421st years, but it does reach the end. Here's a visualization of a much less extreme example. The red ball is moving at 1 centimeter per second, but the rope is stretching at 2 centimeters per second. The basic reason why the ball does reach the end eventually is because the band is not stretching away from the ball. The ground the ball covers is also stretching. So whatever distance the ball has covered is never canceled out. Or how about this analogy? Let's say you walk up an escalator at 3.1 kilometers per hour, but the escalator is going down at 3 kilometers per hour. Eventually, you will reach the top. An outside observer would conclude you are only moving at 0.1 kilometers per hour, even though your true speed is greater. So your true speed doesn't predict how fast you make it to the top. Your speed relative to other things does. Although light from other galaxies is moving towards us at light speed, space expands so rapidly that by the time we see that light, the distance in light years between us and the galaxy is much greater. It's not an illusion, it's a quirk of physics. The galaxies don't appear 45 billion light years away, they really are. 13.77 billion years is just our time window for how old they can be to be visible, and also the maximum distance they can be away from us to be observed at some point in the future. I know that's confusing, and maybe my analogies didn't help, but that's the best that I, a biology major, could come up with. If you Google size of the observable universe, you get about 90 billion light years. That's 45 billion light years in all directions. So what would you see if you teleported to one of the galaxies at the edge of the observable universe? Would you see the edge of the universe? No, you would also see 45 billion light years in all directions. That's why it's called the observable universe. For all we know, the universe literally never ends. Or maybe like the planet, as you travel in a straight line for billions and billions and billions of light years, you end up where you started. We don't know. Next time, we are going to do a little perspective taking. I want to look back at Earth and put its place in the universe into some context, and say goodbye. That will be the end of quite an amazing journey we've been on. Thanks for watching.